Hello and welcome back to my channel. So here we are in part 5 of the ultrasound listening device, aka BAT detector. And here we'll discuss the mixer modulator component of the unit. And in the previous video we discussed the frequency adjustable local oscillator. And prior to that the high pass filter and microphone preamplifier package. So in this video the mixer modulator is what I consider to be the heart of the unit, where all the magic happens, where all the frequency translation occurs. And we'll look at the chip that I'm actually using, and provide a brief description of how it works. It's basically a Gilbert cell, so some of you might be able to find more detailed information on that on YouTube or on Wikipedia or something like that. And we might, if we have time, keep going and discuss the low pass filter, which is essentially very similar to the high pass filter discussion, where the resistors and capacitors in the feedback network of the op-amp are substituted. Where there's a capacitor, there's a resistor, and when there's a resistor, there's a capacitor. So it's a flipped case of passive components for the low pass filter as opposed to the high pass filter. Okay, and that's about enough for the introduction, so let's go right in and start looking at data sheets and the actual breadboard of the circuit. This is the data sheet of the MC1496. This is the chip I'm using for the modulator multiplier in the ultrasound listener. So it's a little bit older chip, and the version that I'm using is the 14-pin DIP, which is very breadboard friendly. Now, I found out that unfortunately the DIP package is no longer manufactured, but you can get it in the surface mount version, which isn't that breadboard friendly. But nonetheless, this is the version I have been using. And you might be able to find a reseller on eBay if you want to follow along using exactly the same chip. If not, there is a 14-pin chip DIP style package available by Texas Instruments, the MPY634. It may not be used exactly the same way as the MC1496. But nonetheless, it is available in the breadboard friendly 14-pin DIP package. You could also try internet searching for this device by another name, which is also called a 4-quadrant multiplier or a transconductance amplifier. It's also known by those names. So if you're not committed to using this one. Okay, so we'll move along to the manufacturer's recommended circuit configurations. And the one I've chosen to use is right there. The balanced modulator for the 12-volt DC single supply. Since just about everything I'm using in this project, I'm committed to using a single supply voltage as opposed to dual supply voltages, say for example here with a plus 12 and minus 8 volt DC on pin 14. So this is it. In this configuration, the local oscillator is applied at this point here, goes into pin 10, and manufacturer recommends 60 millivolts RMS input. the modulating signal to be modulated, input here through pin 1, and it's recommended 300 millivolts RMS. So my oscillator that I'm using is the VM bridge oscillator, which outputs 3 volts peak to peak, and that's a bit more than 60 millivolts RMS, and we'll see what we can do to limit the current going in into pin 10, which might just be a matter of providing a resistor in the input path right here. The gain of the circuit is, the output gain is determined by this resistor between pins 2 and 3, and that's another idea where you can reduce the gain by increasing the value of this resistor. That'll require a harder, larger amplitude input signal to drive the bases of the transistors to achieve the same desired output. So I might try that, and I might comment on how well it's done. There is an important adjustment that is done at this pin, this potentiometer here, connected to these series of resistors between 1 and 4, and that is to null adjust the carrier from appearing at the output. So in the absence of an input signal, you don't want the carrier to feed through the output, because well, it's going to introduce if it's in the audible range, it'll introduce an audible hum, and also loads the audio amplifier in subsequent signal processing stages. Okay, let's move on to looking at some of the internal circuit configurations. Let's briefly have a look at the actual circuit that constitutes the MC1496. So going down on the manufacturer's data sheet, you'll find this configuration of transistors inside the 14-pin DIP. And I'm going to attempt to explain a little bit qualitatively how the multiplication is achieved between the signal source and the carrier or oscillator. So it contains transistors that basically act as analog switches that can be on, off, or halfway in between. So they can be fully on, fully off, or something in between, hence the word analog, depending on the control current that's applied to their bases. So the I sub S is the base current applied to the base of the first row of differential amplifiers, and is the signal current. So they're meant to be used in a differential operation, which means if this signal current is swinging positive, this one should be swinging negative. In reality, if you look at the circuit schematic provided on the data sheet, one of these is actually held at a constant bias, and only one of these inputs is actually used for the signal source, and also for the carrier or local oscillator control current or control signal. So the key point to note in all of this is that this transistor or this transistor, along with these pair of transistors in the upper branch, forms a series circuit or a series analog switch. And for it to pass current up through the collectors, both of these branches, in series branches, need to be conducting. In other words, if you don't have signal current, whichever input you choose, and carrier current, you won't get output out of it. So that's the key. Series switches both need to be on or turned on somewhat to produce an output. And series sort of implies multiplication, just like series logic implies the AND operation and implies a multiplication. So the upper branches are again connected in sort of an OR fashion to produce a inverting output, non-inverting output. It's called inverting because the actual current will increase out of this branch, but since it's connected through a load resistor to V plus positive, the voltage drops on the load resistor as the current increases, so the signal swing is negative, hence the negative label. It helps to imagine these signal currents and carrier currents as being changes about a fixed or static bias level rather than absolute values. So the circuit needs to operate at a bias level, but that is just a DC constant, and just to ensure a linear operation of the transistors. So I hope that gives some insight into the operation of how the MC1496 Gilbert cell operates. I'm sure you can find on the internet some, or not even internet, or even on YouTube, some better and longer discussions on the Gilbert cell. Well, here we have the circuit schematic of the mixer modulator. So it turns out that I did not really make too many changes to the MC1496 recommended circuit configuration over the manufacturer's recommendations. The only thing I did add, well, it's right here, although I labeled it wrong, is a 1.5K ohm resistor, that's 1.5, in series with the oscillator input. And the manufacturer's input recommendation was 60 millivolts RMS for the carrier frequency. The oscillator is the carrier. My oscillator, the VN bridge oscillator discussed in the previous video, is about 3.3 volts peak to peak. So adding this resistor in series reduces the current drive that goes into pin 10, and prevents the transistors in the 1496 from going into nonlinear operation. I also stuck with the 1K resistor between pins 2 and 3 that essentially sets the gain. Going with a larger value of resistor, I found that yes, you reduce the gain, you need to drive the input pins with a larger signal swing, but you get into issues of nonlinear operation with larger signal swings of the input signal and of the oscillator. So the best way to do it is essentially reduce the current that goes into pin 10 from the oscillator with a 1.5K ohm resistor, and you're off to the races. A lot of these small resistors between the pin 10 and 8, and again between 1 and 4, since this is originally meant to be a RF circuit application, these are, I believe, reflectance or impedance matching resistors to match more or less the transmission line impedance that's coming from the signal sources of the oscillator and the signal source. Now, since we're dealing with audio frequencies, usually reflectances are RF reflectance is not really an issue. I stuck with the recommended values of these resistors. I haven't played around with them to see if I could change their values to improve the performance in any way. It seems to work pretty much pretty good the way it is. So one additional enhancement that I did make is, instead of taking the output from pin 6 or pin 12, which are two pairs of outputs, either an inverting or a non-inverting, I decided to run them into a differential amplifier, the TLO74, 1/4 of the TLO74 package, and make use of both of the outputs, where I believe this configuration will reject some of the common mode noise coming from pin 6 and pin 12 and have a quieter circuit in the absence of microphone input signal. This circuit down here, the 2N3903 transistor, this is basically a voltage source. It provides a almost a constant 6 volts DC bias to this resistor network, and the objective is to have the pin 5 of the TLO74 float at about 50% of the power supply voltage being 12 volts. It's around 7.38 volts, which is pretty good. It's close enough. Both pin 6 and 12 of the MC1496 float around 8.5 volts DC bias, and when the 8.5 and the 6 is combined in this resistor network, you get about 7.38 at pin 5, which also appears at the output of the TLO74. So the output of the TLO74 is, ideally we target halfway to the power supply, and this is close enough to be able to provide a reasonable, output swing amplitude. So that's about it for the circuit configuration. It's perhaps the more complicated components of this project. On the whiteboard, this differential amplifier was not included. The whiteboard basically just showed the MC1496 with output taken from pin 6. That would be the case, or 1 or 12. So the mixer modulator block diagram of the whiteboard actually comprises of the MC1496, along with the differential amplifier 1/4 of a TLO74. Okay, here we have the oscilloscope display of the output at pin 7 of the differential amplifier of the TLO74 in the previous circuit schematic. This is the VM bridge local oscillator trace at 3.08 volts peak to peak at a frequency of 71.8 kilohertz, and of course we can adjust that. Let's see, this is all set on single shot right now. If you look at it in real time, that's what it looks like. Okay, it's a lot nicer to look at it that way. Okay, so the local oscillator frequency in this case represents the carrier modulation frequency, and the input signal frequency is about 1 volt peak to peak at 5 kilohertz, supplied by a function generator. So the beats are basically the 5 kilohertz tone multiplied by the oscillator frequency. So it's already, the MC1496 is already offset adjusted, or carrier null adjusted. We can actually have a look and see that we get a reasonably flat yellow trace if we turn off the function generator and do a single shot again. Yeah, there we go. So for a zero input signal to the MC1496, we don't get any of the carrier frequency showing up, and it's both its carrier nulled, and also the fact that we're using a differential amplifier in the TL074 that also helps us in nulling out any residuals left over in the pin 6 and 12 of the MC1496, residuals of the carrier, that is. Okay, so we'll turn the function generator, which represents our signal frequency at this time, back on, and there it is again. Okay, so that sort of demonstrates the operation of the MC1496 mixer modulator. It certainly does what it's intended to do. So just to wrap up the key components of the ultrasound listener, I'm just going to briefly describe the low-pass filter component that's always shown on the as a block diagram on the whiteboard, basically here it is. I'm not going to go into details of the discussion behind it, but this is essentially all the discussions that applies to the high-pass filter that I described previously also applies to the low-pass filter. And you can always go to the Okawa Electric Design website and find out the details of how to compute the components, the resistors and capacitors in the feedback network of the op-amp. The difference between the low-pass filter and the high-pass filter is the positions of the resistors and capacitors are reversed. And this branch here at the input section provides a voltage bias, 50% power supply voltage that feeds through across these resistors and to pin 3, the positive non-inverting input of the TL074. So the for DC bias, the capacitors all act as open circuits as if they're not there. So this is a third order filter, which has a cutoff frequency at 16 kilohertz, and its output drops by 18 dB per octave beyond the cutoff frequency. So that's about it. Not really deserve too much effort in describing this, because it's already been described as the high-pass version in one of the previous videos. I don't remember which, but there you have it. So subsequent videos that I'll do, I'll focus on improvements to the functioning of this circuit, and namely, I think I will do some research in obtaining a good high-frequency microphone, ultrasonic frequency microphone, that is. Hopefully it won't cost me an arm and a leg. Of course, there are gadgets out there that are very inexpensive that claim to be able to listen in on bat frequencies at 100 kilohertz thereabouts. Although I find that some of the ultrasonic microphones that have frequency ranges to the 100 kilohertz are they're priced $1,000 plus. Let's put it that way. And some of these other gadgets that supposedly work at those high frequencies are priced in a couple $100s. So I don't know what you get for that price. Okay, so that about wraps it up for now, and I will be back.